So now we have Young Chen Go to present her as the Bayesian additive regression trees for non-ignorable missing data. So she's a fourth year PhD candidate at Maynooth University in Hamilton Institute. And I'm delighted that she had to present to us, and the floor is yours. I think I can hear you.
Hi, Gabrielle. Can you hear me?
Yeah, we can. Yeah, perfect.
Okay, I'll try
Share your
it.
screen. Is that okay?
My screen. Can you see my screen?
Absolutely. That's perfect.
Can you see it in presenter mode or?
Yeah, we can see it. Yeah.
You also see my cursor?
Yes, I can see everything.
Perfect.
Okay, thank you.
Oh, thank you so much for inviting me to speak, and also thank you, Claire, for that presentation. It's a bit scary to follow that because that was so good. I am going to. Yeah. Okay, so yeah, hi everyone. So like Gabrielle said, I am a fourth year PhD student here at Maynooth University. My supervisors are Professor Andrew Parnell and Dr. Keith Murphy. And my PhD is funded by SFI. So this is just, these are my supervisors, in case you don't know what they look like. So today I'm going to be talking about my research, which is on Bayesian additive regression trees for non-ignorable missing data. So the motivation behind this work is this data set that we have. It has 5 continuous response variables that correspond to some leaf traits, such as specific leaf area, light saturated photosynthetic carbon assimilation per unit leaf area, and so on. And there are 46 continuous predictors that correspond to like soil properties and climate properties, such as mean annual precipitation, relative humidity, silt content, and total nitrogen content. So altogether, we've got 2,368 observations, but only 217 of them are actually completely observed. So this is a snippet of what the response variables look like. These are the 5 responses. There are lots of missing values. And the predictors are fully observed. And sorry, this plot here is the missing data pattern for the response variables. So here, each column corresponds to the 5 different variables. Each row shows like the missing data pattern. So the first row here shows that there are 217 observations where all 5 variables are observed. In the second row, we've got 563 cases where P area is missing and the other 4 variables are observed, and so on. And there are 8 cases where all 5 variables are missing. So if we want to model this data set, we could just throw away most of the data and use the complete cases and run like some multivariate analysis. Or we could run like a univariate model on each column using only the available cases. But maybe there might be a better way to model this. So before I get into that, I'm first going to talk about missing data. So sorry, this is the outline of the rest of the talk. So I'm first going to talk about missing data. So I'm going to introduce the missing data mechanisms and also what a selection model is, and also go through briefly what the probit regression model is like. And then I'm going to talk about Bayesian additive regression trees. And then I'm going to introduce our 2 joint models for fitting multivariate missing data. And then I will talk about 2 simulated data examples, and then just some results from analyzing the plant data. So first off, missing data. So there are 3 different types of missing data mechanisms. The first one is missing completely at random. That's saying that the probability of your data being missing doesn't depend on the data at all. So it just depends on some parameter psi. The second one is missing at random, where we say that the probability of data being missing depends only on the observed data, so the y-obs. And the last one is missing not at random, where the probability of data being missing depends on the missing data itself. So for example, we say like maybe higher values of y are more likely to be missing. So when the assumption is that data is missing not at random, it is important that we take into account the fact that it's missing. And so we have to basically jointly model the missingness and the data itself. And there are two ways to do that. So the first one is using the selection model. That's using this factorization of P of y and m. So the first part is P of y, and the second part is the missingness given the data. And the second model is the pattern mixture model. But we won't get into that today. So what we're using is the selection model. And first I'm going to talk about this missing data model here, which could follow a probit regression model. So the probit regression model looks something like this. So we say that the probability that this binary variable m equals to 1 given some data follows the standard normal CDF. Here Z is, say, a vector of covariance. So our data is the intercept, and then they're the x's and the y's. And B here is a vector of probit regression parameters. So it is possible to motivate this model using like some latent variables. So we introduce latent variables m star, and we say that m star equals to z transpose b plus some error, and with standard deviation equal to 1. And then our m equals to 0 if m star is less than or equal to 0, and then m equals to 1 if m star is positive. And in the Bayesian setting, we can apply like a prior to B and then make like posterior estimates of B using a Gibbs step, and also like sample m star via Gibbs as well. Just to link this back to the missing data mechanisms that I talked about earlier. So if we expand the Z transpose B, we get, for example, B1 plus B2x plus B3y. So if B2 and B3 both equal to 0, then our probability of m equals 1 depends only on this parameter B1 and not the data itself. So we can say that we have a missing completely at random scenario. If B2 is non-zero, but B3 is equal to 0, and x is fully observed, then we say that this probability depends only on the observed data, and so we have missing at random. And if B3 is non-zero, then the probability of m equals 1 depends on our missing data itself. So we have missing not at random. So next I'm going to talk about the data model, which follows a BART model. So Bayesian additive regression trees, it's also known as BART. It was developed by Chipman, George, and McCulloch. It is basically a non-parametric sum of trees model made up of an ensemble of binary decision trees, where each tree acts as a weak learner for the overall model. So BART is known to be able to handle like, high-dimensional predictors and complex interactions between them. And it also has regularization priors to prevent overfitting. This is the mathematical form of the BART model. So we say that y given x and some parameters theta, so normal distribution, and the sum here is the sum of trees. So we've got k trees, and tau here is the precision term. So here we've got the priors of the tree structures. T of k is the kth tree. And Q of k is a set of terminal node parameters, mu of k, and yeah, tau is the position. So, sorry, yeah, these are the priors of the tree structure. The first product term is the probability that a terminal node is, a node is non-terminal, and the second product is the probability that the node is a terminal node. And then we apply a normal prior to the terminal node parameters, and then a gamma prior to the precision term. So just to kind of illustrate how the BART model works, I've got like this very simple data example. I've got one response variable y and two x's. So got a continuous x and a categorical x here. And let's say that we fit a BART model using two trees. So in the first tree, we've got this structure here, and we've only split like a node once. And we're splitting on the first x here. And then in the second tree, we've got two splits. So we're splitting on x1 and x2. So let's say we want to get an estimate for y1. So in the first tree here, we're splitting on x1. So the x1 is greater than 0.5. So we go to the right. And so our y1 kind of falls into this second terminal node here, which is assigned some parameter mu1. And in the second tree, our x1 is greater than 2, so it goes to the right. And then our x2 is equal to b, so it goes to the left. And in this terminal node, it's assigned some parameter mu2. And then we sum up the mu's for those for the observation. So mu1 plus mu2 gives us an estimate for our y1. BART also has a probit model, so it also works for binary data. So let's say now our y's are binary instead. It is similar to the probit regression model, so we can transform it into like this latent space. So we can introduce our y star, and we say that the probability that y equals to 1 follows some standard normal CDF with the sum of trees function. And y star is normal, mean equal to the sum of trees, and precision equals to 1. The priors are similar, and now we don't have to apply a prior to tau because we don't have tau anymore. So now I am going to introduce the two models that we've come up with for dealing with non-ignorable missing data. And I'm going to introduce them in the multivariate framework, but you know, to reduce it back down to like the univariate framework is not too difficult. So in our first model, we call it MIS-BART probit. So we model the data, we model our y's with a BART model, and the missing data indicators with a probit regression model. So y is a multivariate version of BART. And in the terminal nodes now, we have like a vector, mu, instead of just a scalar. We assign a p-variate normal prior to mu, and then now we have a precision matrix omega, and we assign a Wishart prior to omega. For the missing data indicator, this is a multivariate version of the probit model, and now our B is a matrix of probit regression coefficients, so we can apply a matrix normal prior to B. And here we have R, which is a correlation matrix, and we use the parameter expansion for data augmentation strategy for estimating the correlation matrix, but I won't get into that today. In the second model, we've got a multivariate BART model for the data and a multivariate BART probit model for the missing data indicator. So for the missing data indicator, we basically have like a multivariate version of the BART probit model, which also is similar to the multivariate version of the probit regression model. Here we fix the correlation matrix as an identity matrix. Now just to go through the two simulated data examples. So in the first example, I've simulated some data from the Friedman function. So this is just a univariate example. So y equals to this function. And I've made some of the data go missing. So this is the distribution of the data. So m equals to 1 represents the observed data, m equals to 0 represents the missing data. So I've basically made a chunk of the data in the middle of the range of y missing. And in this example, we've got 53.3% of observed data. So if I fit both of our models to this data, I can get predictions for the observed values, and I can get like posterior samples of the missing values, and I can compare them with the true simulated values. So I've split them into training and testing sets. And if I run my models and get my results, this is what they look like. So the top row shows the results from MISBART probit, and the second row shows the results from MISBART 2. On the left, we've got the in-sample observations, and on the right, we've got the out-of-sample. The x-axis shows the predicted y's, and the x-axis shows the true y's, and the y-axis shows the predicted y's. And this is just the diagonal, like 0, 1 line. So the blue points are the observed data, and the orange points are the missing data. So we can see that both our models actually did really well with fitting the observed data and also with making like imputations for the missing values. We can see that the second model, so MISBART 2, actually does better than MISBART probit, but both of them do reasonably well. So we also tried comparing these two models with, say, running a BART model on just the complete cases and making predictions afterwards. And also using mice to impute the data first and then running a BART model on the imputed data set. So I'll show you some results from that. This plot shows you the out-of-sample RMSE values. That's shown on the y-axis, and on the x-axis here, I've got different observed probabilities of the data. So because the data is simulated and they all, like, each observation has a probability of being observed as well. So what I'm showing here is like a threshold of the observation probabilities. So say at 0.1, I'm showing the RMSE values for the data with observation probabilities less than equal to 0.1. So the RMSE values for the data that are less likely to be observed. And then at 1 here, that's all of the data, basically. So it's the data with observation probability less than equal to 1. And here I've got the 3 lines showing the RMSEs for MISBART 2, MISBART probit, and BART on the complete cases. And previously I mentioned that we also tried imputing the data with mice first and then running a BART model, but the RMSE for that was way higher. It's like 4 or 5, so I just removed that from the plots. But yeah, we can see that MISBART 2 does better than running BART on the complete cases, but misspec probit is not as great, but still decent. And for the second example, I've basically got the inverse. So the data in the extreme ends of the range are missing, and only the data in the middle are observed. So again, if I run both my models and get predictions, this is what it looks like. So here it's fitting the observed values pretty well. And it's also making decent estimates for the missing values on the extreme ends. Again, we can see that for misspec probit, it struggles a little bit to capture the missing values on the extreme ends, whereas for misspec 2, it fits much better. But again, both do pretty well. And comparing it with the complete cases part here on the blue line. So again, misspec 2 does well for all the different missing probability thresholds. For misspec probit, we can see that for like the observations that are less likely to be observed, or the data that's less likely to be observed, it does slightly better than the complete cases part. But other than that, it's pretty close. So I'm just going to quickly go through some results from running our models on the plant data, so on the multivariate data set. Sorry. So if I fit our models on that multivariate plant data set, I can also get the predictions for the observed values and plot them against the true, this is on the log scale, so the true values of the 5 variables on the log scale. So they fit pretty well. And I can also check the imputations from our models for the 5 different variables. So here I'm plotting like the distributions of the predictions for the observed data, and also the distributions for the missing data imputations with 5 variables. And we can check to see if the distributions differ like drastically or so. And then if I run the misspec probit model, I can also check the posterior estimates of the B matrix, so the probit regression parameters, to see like what sort of, say, missing data mechanisms are present. So this is just an example. So here I'm plotting the posterior estimates of the B matrix, but only the values that correspond to like how the y's affect the missingness of the y's, basically. So if we look at this GS SLA here, this error bar, so GS SLA basically represents how the values of SLA affect the missingness of GS. And here the error bar overlaps with 0, so we can say that there's probably no effect. Like the values of SLA aren't really affecting how GS is observed or missing. And here for P area dash P area, that is this error bar here, that tells you how the values of P area are affecting the missingness of P area itself. So this error bar doesn't contain 0, so it in a way could suggest that higher values of P area are more likely to be observed. Does that make sense? But yeah, these are just some initial results. There's still work to be done for this real data example. And yeah, these are some references.
Thanks a million. Super interesting talk. Do we have any questions? I think we have time for one question, maybe. Have any question from the floor?
Can I ask a question?
Of course.
Yeah, so thanks for the nice talk. So just wondering whether there's a way to do a goodness of fit check for your missing data model.
Goodness of fit check for the missing data model, like what to say if maybe it is fitting a missing knot at random.
Yeah, so whether your assumption of the linear form of the missingness, whether that's a reasonable assumption.
Yeah, I mean we probably still need to do some work with, like, say, the simulator examples to make sure that it's truly capturing like the real missing data mechanism. We have run quite a few examples, but yeah, there are more checks to be done.
Thank you.
That's great. Any other question? I think we have like 1 minute there for the other talk. If not, I have one very quick about implementation. So I see you planning to create a package with what you're creating there.
Yeah, well, we've
That's
kind of
great.
started on that, or like we're close to finishing or like wrapping up the package.
nice.
There's still some things that need to be tuned and like some default values that need to be set for the priors.
That's fantastic. Looking forward to it. And again, thank you so much for the presentation. It was very, very interesting. I think we'll pass to Sharon for sharing the next section. And thanks a million.